Hello everyone, my name is José Salgado. I'm gonna do the presentation of our paper called the Maximization of Solar Power Extraction from Photovoltaic Modules using Energy Harvesting Solutions for Smart Cities. The authors it's me, José Salgado, Vitor Monteiro, José Gabriel Pinto, Ruben Figueiredo, João Afonso e José Augusto Afonso. For the context and motivation. It was made a weather station. In this case, the weather station has the objective to correlate the ambient data with the power produced by the photovoltaic modules. In this case, the weather station integrates three photovoltaic modules, one made of monocrystalline silicon, another from polycrystalline silicon, and another from amorphous silicon. All the data gathered from the modules and the sensors are stored locally and then transferred to a client using the Bluetooth Low Energy connection. These are some of the characteristics of the photovoltaic modules integrated in the weather station. In this case, the monocrystalline and polycrystalline photovoltaic modules are very similar. The amorphous module, as expected, can't exhibit the same characteristics with around the same area. Although we tried to get the same area of the modules, we couldn't do that, but in the end we're going to take that into consideration when correlating the power produced with the modules. To maximize the power extraction from the modules, we had to use a converter dedicated to that. In this case, we saw some of the converters that exist in the market, and the LTC 3129 was the best, taking in consideration the characteristics of our models. This model uses the MPPC technique and has a topology of a buck boost. This is the circuit using the LTC 3129 converter. In this case, it would be used a circuit for each module. The components of the circuits were selected following the datasheet of the module of the converter. These are some important equations when designing the circuit that we need to take into consideration. The first one is the equation to set the MPPC reference voltage. The second equation is if we want to program the output voltage. Both of these equations can be set using simply a voltage divider on the MPPC pins and the output pins. We can also calculate the feed-forward capacitor with equation 3. And the last equation, equation 4, is just to calculate the power produced, taking into consideration the output voltage and the load of the system. To simulate the modules and the converter, we use the program LTSpice. In this image, we can see the circuits, the equivalent circuits for the amorphous module in the left side, and for the monocrystalline and polycrystalline modules on the right side. Each of these circuits are composed by a current source, a diode, and two resistors, a series resistor and a shunt resistor. Each of these component values were fine-tuned, so we could have the same characteristics of the modules we use on the weather station. This is the power versus voltage graph for the monocrystalline and polycrystalline module. In this case, it was done a DC voltage sweep from 0 volts to 6 volts. And as we can see, in our simulation, we could get the same characteristics of the models we have in the weather station. In this case, with maximum power point with 5 volts and around 1 watt. This is the same type of graph, power versus voltage graph, but this case for the amorphous module, and we could get about the same values of the real module we used in the weather station. In this case, with 3 volts in the maximum power point and around 600 milliwatts of power. We added a 50 ohm load to the output of the monocrystalline and polycrystalline equivalent circuit. And as we can see, the output power, it was only 624 megawatts, and the voltage was way above of the maximum power point voltage. In this case, it was 5.58 volts, which is not optimal. So to maximize the power extraction from the module, we placed the converter LTC3129 between the equivalent circuit of the photovoltaic module and the load that we use of 50 ohms. And then we simulated in a transient simulation from 0 to 6 milliseconds. We also did the simulations for various reference voltages, so we can see the impact of the MPPC reference voltage on the power extracted. This is the obtained results by varying the MPPC reference voltage. And as expected, when we have a reference voltage of 5 volts, it's when we have the maximum output power, in this case 921 volts. For other reference voltage, we can see that the output power is lower. In this case, for a reference voltage of 4 volts, we only obtained 741 milliwatts of power. In this table, it was used the same load. This is the graph for the best case in the table. In this case, for the reference voltage of 5 volts, and as we can see, we obtained very close to 1 watt, which is the maximum power of the actual model that we used on the weather station. And the output voltage almost hit 7 volts. There is also the case when the photovoltaic model is not in ideal conditions. In this case, during the day, it could be raining, or the sun is not as bright because of the clouds. So in that case, the reference voltage of the maximum power point voltage of the module could not be 5 volts, could be a bit lower. But we had to set a reference voltage at the beginning when designing the converter. So that's a case when the limitation of the MPPC technique is that we have to set a reference voltage, and it's always that reference voltage, but it could happen that the module is not in ideal conditions. In this case, we changed the equivalent circuits of the modules to simulate a module that is not in ideal conditions, so that maximum power point voltage is only 4.5 volts. And as we can see, when we have a MPPC reference voltage of 5 volts, in this case we only obtain not even 600 milliwatts. But if we change that reference voltage to 4.5 volts, the output power increases to around 700 milliwatts. For the conclusions, the paper presented the design and simulation of a circuit that maximizes the power extraction from photovoltaic modules. We use the LTC3129 DC-DC converter, which implements the MPPC technique. The simulations were developed using the free software LTSpice. As expected, the DC-DC converter always tried to maintain the input voltage close to the defined reference voltage, and so the MPPC technique was validated. when the reference voltage was set to the MPP voltage of the monocrystalline and polycrystalline module, there was an increase of 47.6% in the output power in the load when using the converter. So the maximization of power extraction from the PV models was confirmed. Thank you for your attention.